Hi, my name is Connor Bush. Today I'm going to be talking about adiabatic flame temperature, what this means, and we're going to derive some equations and then ultimately find the final temperature for our system. And our system here is simply just a combustion reaction where we have air and fuel going in and then a flame coming out with carbon dioxide and water vapor. So all of this is essentially just gas. We're interested in this flame here and its temperature. We'll just say that the temperature going in is 298 Kelvin, and our final temperature is going to be 2000 plus Kelvin. So we know that the flame is adiabatic, meaning there's no heat gained or lost between this whole reaction. Essentially, the change in heat ends up just being zero. We're also at a steady state, which means there's no overall change in mass between the mass going in of the feed and the products, the mass of the products going out. So our fuel is going to be a mixture of methane, ethane, and propane. Methane is CH4, ethane is C2H6, and propane is C3H8. For the air, we're going to just use whatever's in the atmosphere, and that's comprised of only 21% of oxygen and 79% nitrogen, with other trace elements that we are not going to worry about. So in the air, we have the oxygen going in, and then we're going to have the ratio with the nitrogen, and then this all reacts to form carbon dioxide, water, and again the nitrogen is going to come out. So essentially all three equations are the same, just taking into consideration stoichiometry. So we're going to have to balance these equations. Starting with the first one, you can look at the carbons, one carbon here on each side. There's 4 hydrogens on the left, so we'll give the water a coefficient of 2. So on this right side, now we have 4 oxygens, and give this oxygen 2. However, we also need to give the nitrogen 2 because it is in the same ratio for the air composition. So the second equation with ethane, we have 2 carbons on the left, so that means we're going to need to put a 2 in front of the carbon dioxide. We have 6 hydrogens on the left, so I'll give water a 3. So on the right, we have 7 oxygen. So if we do 7 over 2, multiply O2 by 2, we're left with 7, so 7 and 7 on both sides. And then again, we're going to have to multiply the coefficient of water with nitrogen as well. So for this last one, for propane, we have 3 carbons. So we'll multiply carbon dioxide on the right by 3. Hydrogens on the left, we have 8. So we'll multiply water by 4. So on this right side, we have 10 oxygen. So we'll give this a 5, this a 5, this a 5, and all of these equations are balanced. So looking at the idea of the steady state, we know that the small change of mass going in equals the small change of mass going out. And if we tie an enthalpy into this, we see this equation And then essentially the masses cancel because they're equal. So we know the enthalpy going in, what's the enthalpy going out. However, since we are going from this temperature here, 298, to over 2000 Kelvin, that's a pretty significant temperature change. So we're going to have to add the specific heat. However, again, since this is over such a great change in temperature, we're going to have to integrate this with respect to temperature from our initial to our final. And this specific heat is not constant across this great temperature change, so we're going to have to use an equation that we can look at on ChemCAD. It's equation 107, page 36, I believe, right here. So looking at this equation right here. So we have a constant A, B, C, D, and E. And what we want to do is we want to integrate this. So I'm going to copy the equation into my notes. So then we can integrate it on Wolfram alpha because it's so complex to do by hand. And it's not important to understand how to do it by hand necessarily when we have technology like this we can use. So we're going to integrate. I'm just going to integrate this section here, c over t divided by the hyperbolic sine of c over t squared. So I'm going to have c over t divided by the hyperbolic sine of c over t. And all of this is going to be squared with respect to temperature. So we get the constant c times the hyperbolic cotangent of c over t. So I'm going to copy this over into my notes. So when we integrate, we have the constant a times the temperature plus b times c divided by the hyperbolic tangent of c over t. So this is this part of the equation. And then if we go back and just change this part to hyperbolic cosine, we see it's negative now, the constant times hyperbolic tangent of the constant over t. So we have minus b times e times the hyperbolic tangent of e over t. And this is our equation that relates the specific heat and puts it in with the enthalpy for the big change in temperature from the feed to the products. So now that we have this and our stoichiometry of the formula balance, we can go into Python and start to determine ultimately what the final temperature of this flame will be, as we do not know specifically what it will be, with the system being adiabatic and steady state, taking all of this into consideration. Okay, so now we are in collaboratory. We're going to work through a little bit of coding to find out what the final flame temperature will be for the adiabatic steady state system. Here at the top, we just have this module with information about different compounds. NumPy will be one of the modules we use for calculations. We're using this root plugin to ultimately use that to help solve our final equation. This is just for this module here, so we can get the properties and ideal gas constant. So first we're going to establish what compounds we're going to use, and we can do this by saying this. So first we're going to say methane, ethane, propane, and then our air, which is oxygen, and nitrogen. And then we have our carbon dioxide and water. We can also establish here that our beginning temperature will be 298 Kelvin. So next we can create a function for the specific heat formula that we, or equation that we integrated. This represents the sensible heat change, and call it this for the ideal gas, with one parameter being temperature. It's going to return the equation of the integration of the specific heat that we did. So this, it will look something like this. So this is our A, and then I'm going to copy this because it's going to be used a lot. B times C, and then this right here is divided by the hyperbolic tangent of the C constant divided by the temperature. And this is minus the D constant times the E constant times the hyperbolic tangent of the E constant divided by final temperature. Put parentheses around here. So everything lines up accordingly, and we're going to have to divide by 1,000 because it's going to return our final enthalpy in kilojoules, and we just want joules. So next we can go about how we're going to put in the formula and get the different moles of each compound. So we'll say the fuel formula equals this matrix of the methane, ethane, and propane. So we're going to kind of represent that like this. So that's methane, 1 carbon, 4 hydrogen. Ethane is 2 carbons, 6 hydrogens. And then finally, propane is 3 carbons and 8 hydrogens. The moles of the fuel are desired to be 10 moles of methane, 1.5 moles of ethane, and 1 mole of propane. And we can get the moles of the carbons and hydrogens respectively if we do the matrix multiplication of these two matrices. So let's see if we're good so far. So if we just test, we have 16 carbons and 57 hydrogens within this fuel mixture. So now kind of looking at before with our stoichiometry, the moles of the carbon dioxide always match with the moles of the carbons. The moles of the water was always 1/2 of the hydrogens. The moles of oxygen were the moles of the carbons plus 1/2 of the moles of the water. And then finally, the moles of nitrogen were just the moles of oxygen times the ratio of the 79/21 to represent the composition of the air mixture. So we can say that like this. And this represents all the different components of the formulas that we are using. And now we can combine these, so we have the feed side and then the product side. So we'll say the moles of feed is equal to concatenation of the fuel array, and then we'll have to make another array of so the moles of the fuel represents these first three, so methane, ethane, propane, and then we're going to have to say the moles of oxygen, the moles of nitrogen. We don't have the carbon dioxide in the feed, so we'll have to say just 0, and same with the water. Put a bracket here, and then I will copy this, and similarly for the product side, we'll call it that. Actually, don't need that right there. We're gonna have to make an array of zeros that matches the fuel array, so we can represent that like that. And then we have no oxygen left. We have the same moles of nitrogen, and then we have the moles of the carbon dioxide, and then our moles of water, and making sure that these line up. So this zeros-like array will cover the first three, and then we have no oxygen left, so 0, the moles of the nitrogen, carbon dioxide, and then water. So let's see if this is correct. And that works. So now we can make another function which represents the enthalpy that's outside of the addition of the specific heat. So this is basically just like the enthalpy going in equals the enthalpy going out. However, this one we have to insert the moles and then also the temperature. So it's going to return the dot product between the moles and then the heat of formation of each gas here, each compound. So it has to be a dot product because we're multiplying essentially two matrices, even though the moles is just a single element. And then we're going to add this with the dot product of the difference between the two temperatures with the specific heat into consideration. So we're going to have the final temperature minus the initial temperature. And then it's the dot product between the moles and that. So let's see if that works. Great. Okay, so finally we can make one last function. I'll just call it energy with a vector parameter. The temperature will be the only parameter that we need, and we want this to return an equation equal to 0. So because this is the equation that we're going to put into the root solver, so we're going to use this equation up here to subtract the products essentially from the feed. So the products, the moles of the products is related to the final temperature, and the moles of the feed is related to the initial temperature. So if we use the root solver with this energy equation, and we can just, for our initial guess, we can just say perhaps the final temperature will be the same as the initial. If we run this, we see that the solution converges, it's successful, and this is our final temperature, 2,347 Kelvin approximately. So if we would want to store this as variable, we could just call it final temperature. We can do that. So if we call it, it's still an array, but it's 2,347, and this is in Kelvin. So yeah, thank you.